All right, so, and let me put in this mode. So here's the plan for today. Find it. Okay, good. Okay, so we're gonna use, I think the same like order we used last time works well. So we'll start off with a little bit of discussion lecture. That'll be like, laying out some topics that'll be useful for next week's paper. Here's next week's paper on nonlinear averaging of thermal experience. So keeping with this theme of thermal, and we got into a little bit of environmental variation in this paper. So we'll read this one, and also I think there's a critique that I'll dig up and try and add the critique. And then, yeah. So I'll give you a little bit of background info on that'll be useful for this paper. Then we'll go on to discussing this week's paper. So that's the plan. Okay, so the overarching topic here is variable environments. And this will be part one because I've got plans for the week after that too, which will be competition in variable environments, which is, the theme of the seminar here. But before we get to competition variable environments, I thought it'd be good to build up a little bit slowly and start out with growth in variable environments. And I'm just going to start out with something that should be like familiar to many. The simplest model in population ecology, RF equals MA, as it's been called, exponential growth. So as you all know, exponential growth is unrealistic. It's a density independent model. Either of the species is going to go extinct or it's going to blow up to infinity. And so because it's density independent, that means it's a linear model. Then here it is. Y'all seen this one, right? Okay. So how do you actually solve it? Why is the solution to the exponential growth exponential? Let's just walk through the steps here. So we can scooch the n to the other side. So then the left-hand side now reads the per capita growth rate of species n equals little r. And we can recognize from calculus that left-hand side is the same as the change in the logarithm of the density. Okay, so this is super important. This is why in ecology, I mean, exponential growth, it's a multiplicative process. This is why it's often better to plot populations on a log scale. And we can just imagine this. So we can use this to solve for the dynamics. So the change in log abundance is the initial log abundance plus the growth rate little r times t. So the key thing here is that exponential growth is linear when you look at it on log population size versus time. And this is really useful empirically for estimating population growth rates. It's kind of the natural way to look at growth rate. One thing about it in this form too, that is basically the same equation as the equation for position, like from just like the laws of motion. So instead of thinking about log n being population size, it could be your position along a roadway, and little r is your velocity. It's how fast you're driving down the road. So if you want to know where you are in the future, just look at where you started, look at your rate of speed, your velocity, little r, multiply it by how long you've been driving. That's where you are on the road. It's literally the exact same as that. So it's hopefully all refresher, and we can rewrite this in terms, we can exponentiate both sides to get the familiar exponential equation that we all know and love. Same thing. Okay, variable environments. This is where it gets only a little bit tricky, not too much. Now let's let the growth rate, little r, be a function of time. Okay. And it's still density independent, so there's no feedback from the population on the growth rate. But now, so it's some kind of external forcing, change in the weather, climate, what have you. So that's the only thing different. So we just go through the same steps. Now this bottom graph is showing just some fictitious graph of growth rate versus time. And I just made it piecewise constant because it was easier to draw in PowerPoint, but it could be anything. It could be a periodic function. It could be a random function. It could be basically anything. This is going to be generally true. And so you can imagine now, like we're on the road and we're going forward for a while at a certain speed, and we hit the brakes, put in reverse. We go in reverse for a while, hit the brakes, put into a higher gear, go a little bit faster, and so on. So here, little r at any given instant in time is going back and forth between positive and negative. And you can imagine, just based on that analogy of where you are on the road, you could still figure out where you are at any given point simply by integrating this curve. And so that's the answer here. So we can also solve this. So if you want to know what the log population size is at any given time, again, what the initial log population size was, and then you simply integrate the growth rate up to that current time. So at first we were moving forward, and we put in reverse, went backwards, moving forwards, and so on. Okay. So, this is thanks to this being a simple linear equation that we can solve it. And then finally, we can rearrange that and replace that integral by the average growth rate, r bar. And then we just multiply that average growth rate by the time t. So any questions on this? How we can integrate growth in a variable environment? Okay. I should say that this is true for models in continuous time. For models in discrete time, which we haven't talked about in here, but you might run into them sometime, I want you to be misled. So in models in discrete time, it's kind of the same thing, but instead of using an arithmetic average, you need to use a geometric average of the growth rate. If you use the arithmetic average, you'll make some mistakes. Okay. All right. So wait, where am I going with this? All right. So that's basically warm up part one. R bar, the average growth rate, is basically the appropriate definition of growth or fitness in variable environments for these unstructured populations like we have here. And this is going to be true. Let me add that. So this is going to be true regardless of what the type of environmental variation is, whether it's periodic, whether it's aperiodic, random. This is generally true. Probably if there's a proper mathematician in the audience, they would find some case where it's not true. Maybe if it requires ergodicity, but in general, for everything we worry about, this is going to be true. So what good is this, right? How often do species grow in density independent mode? So the same approach is useful for considering invasion analysis that we discussed for studying competition. So you remember in invasion analysis, you put one species in by itself, let it go to its long-term attractor, sprinkle in the other guy, measure its growth rate, vice versa. If each can grow into the monoculture of the other, then we say they coexist. So this is basically, you use this averaging technique for looking at coexistence in variable environments. This is what we'll see in the paper after the one we're reading for next week. And just, you know, a caveat, it's a little bit more complicated if we're talking about structured populations. So this is what I showed you was true for an unstructured population. That is a population that's just defined by a single number. For structured populations, it's more complicated. If you have an extensive structure like juveniles and adults, where it's all like number of individuals in particular classes, um, then the appropriate definitions of growth or fitness are either flow K exponents in periodic cases or Lyapunov exponents in general. If you have intensive structure, remember intensive structure is something like the nutrient quota that we've looked at last week, and that's in this week's paper. If you have like a nutrient quota, then it's a little bit different. What you do is you run the dynamics of the intensive variables like the quota as forced by the environment. Let that reach some sort of attractor, perhaps periodic attractor if the forcing is periodic. Once it has, then you can like integrate over one period or over, you know, all time the dynamics of population growth. So anyway, it's a little bit more complicated. I wanted to work this out based on this week's paper because they actually have, you know, this is their model fits into extensive structure with external forcing. But I couldn't get their parameter values, so I can't make a nice graph of this for y'all. So, all right, so this is part one, my short warm-up preamble here. Any questions on how to calculate growth or fitness in variable environments?
Chris, is it pretty much always true that intensive structure will be like fast relative to the other variables? And then like, is that sort of what this like is hinging on? And are there exceptions to that that you should be careful
Hmm.
about?
Yeah, that's a good question. Right, because it's sort of like a separation of timescales argument here. Um, and in general, it seems like it shouldn't be true. But I think the trick here is, you know, essentially if you're measuring growth rate when rare, so then you can make the, you know, the extensive variables like the population size or what have you, you can make those arbitrarily small, so that they don't appreciably change by the time the intensive variables reach their attractor. So I think in general it's safe, but you know, of course, it's a mathematical you know, shell game here by making the invader like infinitesimally rare. So,
That makes sense.
all right, any more thoughts on this thing? And I suspect if, you know, I guess if you have both, then you just do the intensive thing and then plug it into the extensive trick. So, okay, so it's well known. It's at least we know how to do this. All right. So part two on my preamble, which will be useful for next week. Um, this phenomenon, this thing called nonlinear averaging, also known as Jensen's inequality. So has everyone seen this? Is there someone who hasn't seen this nonlinear averaging? If you have, raise your hand on Zoom. Okay. If you haven't, raise your hand on Zoom. All right. Good. Couple people. So it's worth talking about because this is also super general, um, and kind of nice. We'll build on this. So basically the idea is we just learned that in a variable environment, the appropriate measure of growth or fitness is the average growth rate, which is what I'm calling here R bar of X, where X is some kind of environmental variable that's changing. Okay, so R bar is really what we're after here. But maybe we're lazy and we're taking a shortcut or we're not thinking too carefully. And we're like, well, we'll just measure growth at the average environment, and that should be good enough. Okay, so that's what this R of X bar is. X bar is the average environment, and then we're just going to measure growth at that one. So in general, these two things are not the same. And the only exception is the only exception. One exception is if R of X is linear. I'm sure you could cook up a case otherwise where it's nonlinear. But definitely, if R of X is linear, they're actually equal. But if they're nonlinear, basically all bets are off. Okay, so let's take an example here. So here's an example of some growth as a function of some environmental variable X. And it's going to fluctuate around some average X bar. And we see that that's kind of the optimum right here. So growth is maxed out there. Now let's let the environment X vary somehow back and forth in this shaded range. Well, what you see then is that when you're at the optimum environment, you're doing great, but then it gets a little bit, let's say, cooler and performance declines. Then it warms up and goes past the optimum, and again, performance declines. So if we're averaging the growth rate over this variation, we can see that it's actually a little bit less than the growth rate at the average environment. So there's a penalty for having environmental variation in this case. That clear for everyone?
Yes, so if I understand well, Chris, if we have, for example, temperature increasing over time at the same rate, we could use the average growth rate measured in an average environment, because then it would be equal to the...
So the thing that needs to be linear is this, response curve, which you can think of it, if this were temperature, this would be a thermal performance curve. So if the thermal performance curve were linear, and then the environment fluctuated around back and forth, then basically the good would just, balance the bad, and they would weigh out to the average. But in this case, yeah, not so much.
Okay.
So it's mostly about the shape of the environmental response function.
Sorry, I didn't get what the shaded area is.
Oh, this is just, you can imagine that X, this environmental variable, is going back and forth in the shaded region somehow.
Okay, so the R bar is basically the value of that specific environment where the X is varying in that area.
Yeah, I mean, it's a heuristic figure. But yeah, you can imagine that, like basically you have these times, if you get out to this extreme, it's really bad. Here it's kind of bad. Here it's great. Here it's kind of bad. Here it's terrible. Those just average out to this R bar. Okay, so environmental variation, it's bad. But is it? Maybe not. Here's another curve. So here's another environmental response function that instead of being unimodal is U-shaped. And now you can see that here I've got it set up so that the average of the environment is right here at the worst. That's the worst performance at this point. So now if it gets a little bit cooler, they do better. If it gets a little bit warmer, they do better. And now you can imagine that if the environment is varying back and forth in the shaded region, then sometimes they're doing okay, not so good, doing okay. This is going to average out to this R bar here, which is going to be a little bit bigger than the growth at the average environment. So, depends. Is environmental variation good or bad for you? Depends on the shape of the environmental response function. And as an approximation, you can approximate the average growth, which is what we're interested in. It's approximately growth in the average environment plus a correction term. And the correction term has two bits. The first bit is the variance in the environment. Oh, maybe there's a 1/2 here, huh? It's the variance in the environmental factor times the second derivative of the response function. Okay, so on this example on the left, if you're at a maximum, second derivative will be negative. So that means that if you're at a maximum, environmental variation will decrease performance, whereas if you happen to be at a minimum or any place where there's a positive second derivative, then environmental variation increases performance. But you know, this is just an approximation. There's more terms, but this is usually good enough. Okay. So this is the big idea behind nonlinear averaging or Jensen's inequality, and super powerful idea. I'll email around a couple, you know, sort of conceptual papers where people are trying to hype it up because it's such a cool concept and a little bit non-intuitive. So, okay, so that is just the background material we'll need for next time. Any final questions on nonlinear averaging? Okay, so this will be useful in the paper for next week, but now move into the paper discussion for this week. So it's this one by Carling Big and Dave Vasseur, looking at interactions between temperature and nutrients with phytoplankton. So I hope you all had a chance to read this. So we've got two parts. I think we'll have 2 rounds of discussion here because I didn't really come up with a lot of great questions to ask about it. So that'll be the first task. So initial discussion section, I'll send you into your little working groups, and you want to discuss with your group these 3 things. First of all, like, were there any like questions about how the paper, you know, the logic of the paper, what they did, and so on. So try and like sort out any questions amongst yourselves about the paper. Second, try and summarize, you know, for the group, what are the main takeaways from this paper? And then you can help me out with the next discussion by coming up with good things to discuss in the second round. I've got a couple, but hopefully you guys come up with some more. Ones I want to discuss are like, you know, you can always, you know, discuss about the assumptions of the model, and what would be possible next steps beyond it. So see if we can add a few things to this list for the second discussion period. So any questions on that? Okay, drop those in the chat. All right, so I'll break us up into 3 rooms. And we can take, say, 15 minutes on the first round. We'll come back together, then we'll see how it goes in the second round. Sound good?